Okay, so on this one, it says a rectangular page is to contain a square 24 inches of print. So that's the printing area. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins left to the right are 1 inch. What should the dimensions of the overall page be so that the least amount of paper is used? So the first thing that I'm going to do here is just draw this out because it seems somewhat confusing. So if we just draw a picture of what we're doing, so here's the page. Then you have the page margins. So at the top and the bottom, it would be like 1.5 inches. And on the sides, 1 inch. So these are kind of what the margins are going to be. That's where within that red part, that's where the printing is going to happen. Where from here to here, that's 1.5. Okay. And then from here to here, that's 1 inch. So then let's call this distance, so from here to here, okay. Let's say that that is L, and from here to here, let's say that is W. And the area of the red is going to be 24 square inches. So now we have a picture. Let's come up with some equations. So first of all, you have the area of the red, right? We know that that's 24. So I'm going to go ahead and delete that. The area of the red, we know that it's 24, and it's going to be length times width. Okay? And then we also have the area of the entire page itself. So that area is going to be, now on this side is going to be length plus 1/2 plus 1.5 plus 1.5, which is length plus 3, times width plus 1 on that side and 1 inch on that side. So then that would be 2. So we have two different equations, and we want to maximize, right? So what should the dimensions of the page be so the least amount of paper is used? So right here, this is the equation that we're going to want to find the derivative of. Okay, so we need to get either L in terms of W or vice versa. So over here, we're going to take this equation, solve for either L or W. It doesn't really matter. So let's divide out the L. So 24 over L is equal to W. And we're going to take this and we're going to plug it right in here for W. And then find the derivative. So if you haven't tried this already, pause the video at this point. You're about 3/4 of the way there. Pause the video, find the derivative, interpret your solutions, find the derivative, set it equals 0, interpret your solutions, come back to the video and see how you did. So when we go through and we plug that in, you get to right here. Then what I did is I multiplied everything out just to make finding the derivative easier. And when I multiplied everything out, it simplified down to the area is equal to 30 plus twice the length plus 72 divided by the length. And there I found the derivative. And the derivative of 30 is 0. Derivative of 2L is 2. The derivative of 72 over L, you could do low d high minus high d low over low low. Or you can derive 72L to the negative 2, however you wanted to do that. Sorry, to the negative 1, not the negative 2. Anyway, you get the derivatives here, set that equal to 0. And when you set that equal to 0, go through and solve. L squared is equal to 36. So our length is going to be optimized at 36 inches. Okay, so At this point, if you haven't done this already, stop the video. You have what the optimized length is going to be. Think about in our original sketch what that represented, and then what questions are being asked, and interpret all of these numbers to write your final solution as if you're going back to the company and saying, hey, if you want to save as much paper as possible, these are the dimensions that you have to use for this particular project. Your interpretation, how you did there. So we know that the length is 6, so we plug that back into the area to figure out what our width is going to be. And remember, that was the width and length of the printable area, right? That's where we're printing, but we want to know the length and width of the overall paper itself. So that's why we needed to, for the width, it was 4, but we needed to add 2 to that to account for the 1-inch margins, and we needed to add 3 to the 6. So our final answer is the overall page length is 9 inches and the overall page width is 6 inches to maximize that 24-inch printing area there on that page. Okay, so let's look at another one, finding minimum length. This is unique because some of these problems, they force you to think outside of the box. And on this one, we're actually going to use a graphing calculator to help us. So first of all, read and understand the problem. Do that on your own. Pause it. If you need to write down whatever you need to write down, I'm going to draw a picture. Go ahead and draw a picture so you can understand what is happening, what is being asked, and try to come up with 2 different, in this case, 3 different equations to help us answer this question. Pause the video and then come back. So here is a picture of my problem. You have a 12-foot post and a 28-foot post, and you're throwing a wire down between them onto the ground somewhere. And the whole goal is to minimize the amount of wire that you have to use, because this wire is made of pure gold, and you don't want to use extra wire if you don't have to. And the distance between those posts is 30 feet. So we have it set up like this. You notice we do have 2 triangles, right triangles. And so we can use that idea in order to write our 2 other equations, because the problem up here is they want us to minimize the wire length, which is a simple equation right there. Very simple. Y plus Z. That's the wire length. However, trying to get y in terms of z or z in terms of y is not possible. So we have to get creative. And what we're going to do is we're going to come up with 2 equations. We're going to come up with an equation for this triangle right here, and then an equation for that triangle. And we're looking at the a squared plus b squared equals c squared, because we know some parts about those triangles. So go ahead and set up those 2 equations, one for the small triangle, one for the big triangle, and see if you can get those to help you move forward in this process of solving this problem. So if we do this, you notice you can get each one of those solved. So the purple is the smaller triangle and the green is the bigger triangle with the z. I can solve the purple for y, I can solve the green for z, and that's helpful because they're both solved for the same variable, which is x. So now what I can do is rewrite the wire length in terms of only x. So you would have the wire length is equal to, instead of y, you would write x squared plus 144 plus, and instead of z, you would write 30 minus x squared plus 784. Okay, so now you have an equation. We can find the derivative of that. And that's totally doable. It wouldn't be too difficult to find the derivative of this, but I want to show you kind of how we can look at these graphs to find the maxes and mins or use that information for optimization problems. So go ahead and graph this on your graphing calculator. See if you can find the max or the minimum, and in this case it should be the minimum if we did it right, because it's looking for the least amount of wire. And see if you can interpret the problem and answer the question that was asked. So from here, go all the way to the end and answering the question that was asked. Pause the video, come back, and once you have done that, come back to the video. Okay, so really, if we graph this thing, it looks like this. And we're looking for the minimum, which is at x equals 9, y equals 50. So the minimum occurs at x equals 9, y equals 50. So what does that mean in the context of this problem? Well, what did they want to know? They wanted to know, right, where should the stake be placed to use the least wire? So the x is super helpful because it tells us the distance from the 12-foot pole. So here's your 12-foot pole. X tells us how far from that 12-foot pole to put that thing. So we are going to connect them or tie the wire to the ground from 9 feet from the 12-foot pole. You can answer that question too, because you could take 30 minus 9 and it's that many feet from the 28-foot pole, but we answered the question to minimize the amount of very expensive gold wire used. You're going to go 9 feet from the 12-foot pole. On this one, I only have about 3 minutes left for this video, but I want you to try this on your own. I'll get you started. It asks, you're using one wire to form both the area, both a circle and a square, and you want to maximize the total of area of both of those, right? So you're going to need a couple equations, and you have a circle and a square. You're going to need the area equation for the sum of those and the perimeter equation for the sum of those as well. And you have 4 feet of wire, so the perimeter is going to be equal to 4. So set up those two equations, and remember we want to maximize the area, so you're trying to get one down to one variable, which would be x, and then the area, of course, that's your other variable, and then solve. You can either graph it once you have it or try to do it algebraically. See, set it equal to 0, either one. So finish this one, interpret, go all the way to the end, pause the video, and come back. So there's a lot of stuff here. I'm just going to go through it really quickly. If you need to pause it, screenshot that so you can get it. Here is me going through it algebraically, going through finding the derivative, setting equal to 0. But once you get to this part right here, you can go ahead and graph it. And this is what your graph is going to look like. If I can get to it. This is what your graph is going to look like. Okay, and you want to find the minimum, which is going to be right here. Now your minimum is when x, so remember we're solving for x is going to be 0.56, and that's what I got back here. And so up here your x value has to be 0.56 in these equations in order to minimize your area. Now an alternate solution, I'm going to stop there, but an alternate solution, if you look back at the graph, it's kind of silly and we should know this already, but an alternate solution would be using no wire on the square and all the wire on the circle, because in reality, right, this 1.237, that represents your area. In reality, that's going to maximize it, or sorry, minimize it, and you're going to get the maximum amount of area, but it doesn't really make sense because you want to use both a square and a circle. So we're going to stick with the 0.56 on this one as our final answer as far as what the x should be. Question, the side length of this square needs to be 0.56, 0.56. That's the side length, so 0.56 plus 0.56 4 times. That's where this piece came from. But if you were curious, like how much is going to be used on the circle, we can come back here, figure out, okay, what is the radius after we plug 0.56 in there, and then use the circumference to figure out how much we're going to be using on the circle. I know that wasn't part of this, but just to extend it in case they ask that question on this particular problem. Okay, that's the end of my videos. I hope this was helpful.